Welcome to this video on the ASTM/ISO classification of additive manufacturing processes. We will explore the standard categorizations, scientific principles, and decision matrices defined by ISO ASTM 52900. This video is tailored for scientists, researchers, and professors in the advanced manufacturing field. We will examine the underlying mechanisms and standardization frameworks that govern modern additive technologies. Our learning objectives for this video are to categorize additive manufacturing technologies into 7 standard families, articulate their binding mechanisms, and evaluate processes using a decision matrix. Let's begin by looking at the framework of standardization, which establishes a universal taxonomy for additive manufacturing. As Terry Wohlers of the ASTM F42 subcommittee notes, industries require strong standards to grow effectively. These consensus standards ensure uniform quality across sectors like aerospace and defense. ISO ASTM 52900 was created to solve the ambiguity in industry terminology. It provides a unified set of definitions, grouping all commercial systems into 7 distinct categories based on their architecture and deposition strategy. The 7 standard categories are Vat Photopolymerization, material jetting, binder jetting, powder bed fusion, material extrusion, directed energy deposition, and sheet lamination. The first category is Vat Photopolymerization, often referred to as VPP, which involves the selective curing of liquid photopolymers. In VPP, liquid photopolymer is cured using light-activated polymerization. Layers are formed by projecting UV light, typically using a laser or DLP, onto the resin surface. The scientific principle behind VPP involves initiators absorbing photons to trigger polymerization. Commercial implementations of this technology include SLA, DLP, and CLIP, DLS. This evaluation matrix highlights the characteristics of VPP, including its use of thermosetting resins, high resolution, and superior surface finish, alongside limitations like the need for post-curing. Moving to the second category, material jetting, or MJT, which utilizes a droplet-on-demand deposition process. MJT functions similarly to 2D inkjet printing. It deposits build material in successive layers, which are then immediately cured or cooled to form the part. For MJT, solidification relies on rapid state changes via polymerization or cooling. Commercial examples include polyjet, drop-on-demand wax printing, and nanoparticle jetting. Finally, this evaluation matrix for material jetting showcases its multi-material capabilities and high resolution, balanced against potential limitations like slower build speeds for larger volumes. Now, let's examine the third category, binder jetting, or BJT. This process utilizes a liquid bonding agent to selectively join powder materials together. In binder jetting, a recoater spreads a layer of powder and a printhead deposits the liquid binder. When working with metals, the resulting green part requires subsequent sintering or infiltration. Binder jetting relies on capillary action to penetrate the powder bed. The commercial landscape includes color jet printing for polymers and metal binder jetting for industrial applications. This matrix outlines key parameters for binder jetting, noting its high throughput and lack of thermal stress, offset by the need for complex post-processing for metal parts. Moving to our fourth category, powder bed fusion, or PBF. This process relies on thermal energy to fuse powder particles into solid structures. PBF involves a laser or electron beam, tracing cross-sections in a preheated bed of powder, fully melting the material to create dense, robust parts. The process is governed by rapid solidification kinetics and heat transfer. Well-known commercial technologies here include selective laser sintering and laser powder bed fusion. This evaluation matrix for PBF highlights its ability to produce highly dense parts across a range of materials, while also noting the inherent thermal management challenges. Our fifth category is material extrusion, or MEX. This is perhaps the most familiar additive manufacturing process, defined by the deposition of thermoplastic filaments. In material extrusion, feedstock is fed into a heated extrusion head, where it is melted and deposited along a calculated path to build the object layer by layer. This technology relies on non-Newtonian fluid dynamics. Material must shear thin during extrusion and rapidly solidify upon cooling. Common terms include FDM and fused filament fabrication. Reviewing the evaluation matrix for material extrusion shows its accessibility and versatility, though it often requires trade-offs regarding structural isotropy and build speed. The sixth category is directed energy deposition, or DED. This process is unique for its ability to simultaneously melt and deposit material. DED utilizes robotic arms or multi-axis gantries to feed wire or powder into a localized melt pool, allowing for complex, in-situ alloy creation during the print. Fundamentally a micro-welding process, DED is governed by weld pool dynamics. Commercial systems include laser-engineered net shaping, and wire arc additive manufacturing. Let's review the evaluation matrix for directed energy deposition, focusing on its rapid build rate and metal repair capabilities, while noting the characteristic need for extensive machining due to its near-net shape output. The seventh and final category is sheet lamination, or SHL. This process operates by stacking and bonding sheets of material to form a 3D object. Sheet lamination is often considered a subtractive additive hybrid. Sheets are bonded layer by layer, and a laser or CNC mill cuts the contour of the part, carving away excess material as it progresses. For metals, SHL often utilizes ultrasonic consolidation, a solid-state bonding process that disrupts oxide layers using vibration. Commercial examples include laminated object manufacturing, ultrasonic additive manufacturing, and selective deposition lamination. The evaluation matrix for sheet lamination highlights its unique capability for embedding electronics and sensors, contrasted with its typical challenges regarding dimensional accuracy and material waste. Now that we have covered the 7 categories, let's examine the cross-cutting scientific principles that govern all additive manufacturing processes. We can group processes by their thermodynamic profiles. Some involve melting and solidification, traversing the liquidus line, which often leads to residual stresses. Others are solid-state, avoiding bulk melting entirely. When selecting an additive process, it is essential to use a decision matrix to evaluate the specific criteria of your engineering project. There is no single superior process. Engineering selection requires navigating trade-offs between material compatibility, dimensional accuracy, mechanical isotropy, and speed. Aerospace, for example, heavily favors PBF and DED. This matrix helps visualize the relationship between potential materials and the processes capable of handling them effectively, guiding initial technical feasibility studies. Finally, remember the fundamental trade-off. As structural resolution requirements increase, such as requiring thinner layers or finer voxels, the volumetric deposition rate typically decreases. To help navigate the commercial landscape, we can map common proprietary technology names to their corresponding ISO standard categories. Whether you hear SLA, CLIP, PolyJet, FDM, or WAAM, you can always map these to the 7 standard families, ensuring you speak the same language as industry standards. Understanding this standards ecosystem is vital. ASTM Committee F42 is responsible for defining these core additive manufacturing technologies. To wrap up, familiarization with F42 standards, covering test methods, design practices, and terminology like 52900, is necessary for anyone involved in high-level additive manufacturing research and qualification.